Welcome everybody to this second course on MCMC methods. Today we're going to cover chapter 2, so it will be about invariant probability measures, and the keywords will be existence, uniqueness, and reversibility. So let's start. We will first begin by defining what is an invariant probability measure for a Markov kernel. So here is a definition. You consider pi a probability measure, and you say that pi is actually an invariant probability measure for the Markov kernel P. As soon as you have the fact that pi p is equal to pi, okay? So pi p is equal to pi. It is this equality, and just to remember the notation, if you look at what we have done in the previous chapter, I think it's here. We have said that let's say that you have a Markov chain xn starting from u, then the low of xn is actually upn. So if you say that pi p is equal to pi, means that the low of x1 is the same as the low of x0. So when you start from pi, then time 0 you're under pi, and at time 1 you're also under pi. And since, of course, when you have pi p, which is equal to pi, if you apply on both sides pi k, so you get pi k plus 1 here and pi k here, and they're all equal to pi, so the low of any xn, when n is any integer in n, is exactly pi. So that's interesting. It means that if you start from the distribution pi, you stay forever with the distribution pi. So it is explained here in this first paragraph. And actually we can check that if you look at the sequence of variables xk, then it will constitute a strongly stationary sequence, in the sense that xk1, xkn follow the same law as the same n applet with a shifted of p, where p is any integer. So you can shift the time index by p, you get exactly the same law. Okay? So now we have another definition, the definition of reversibility. We say that Markov kernel P is pi reversible as soon as you have this equality. So pi dx p of x dy is the same as pi dy p of y dx. So it is a notation which is infinitesimal, because you have this dx and dy, and you can write down something which is maybe more rigorous. So the pi reversible is equivalent to saying that for any function h which is either non-negative or bounded, then if you integrate this function h of xy with respect to this measure or with respect to this measure, you obtain the same quantity. And actually the nice thing is that as soon as a Markov kernel is pi reversible, then it is also pi invariant. So if you want to check that a Markov kernel is pi invariant, a sufficient condition would be that it is pi reversible. Okay? So the proof is quite easy, quite simple. If you look at pi p of a, so this quantity here, pi p of a, by definition it is the integral with respect to the indicator on y of pi dx p of x dy. Here you can replace it by this quantity thanks to the reversibility, and then you see that you will integrate only with respect to x here, and there is nothing which depends on x here. So you will get only p of y comma capital X, and this is equal to 1 because this is a probability measure. When you integrate probability measure on the whole space, you get 1. So since you have 1 here, what remains is just pi of a. So you're done. Pi p of a is equal to pi of a. So that's very interesting. It means that as soon as you can find some pi reversible Markov kernel, you have also a pi invariant Markov kernel. So now we're going to explain what is the metropolis hasting algorithm. So the framework is the following. You have a probability measure pi, okay, and you know this probability measure only up to a multiplicative constant, and the idea is how to construct a Markov chain which has pi as invariant probability measure. And why do we aim at finding this type of Markov chain is because then if you want to approximate this integral, so it is, the integral is not dx, it is pi dx, so you integrate h with respect to pi dx, then you will be able, as soon as your Markov chain satisfies some kind of law of large number, you may be able to approximate pi of h by this quantity, which is nice in practice. So let's construct the metropolis hasting algorithm. First, we assume that pi has a dominating measure. With respect to this dominating measure, it has a density which is strictly positive. So we will call also pi its density. So you have two notations for pi. It's an abuse of notation, of course. Pi dx is pi of x lambda dx. And we assume also that the Markov kernel, you have a Markov kernel Q, which has also, let's say, transition density, which is Q of xy with respect to the same dominating measure lambda. Okay, and here you have that Q is assumed to be positive, like P is assumed to be positive, Q is also assumed to be positive. Now, the type of algorithm that will interest us is the following. As soon as you have a function alpha, which takes value in 0, 1, so alpha is here, you will consider algorithm 1. Algorithm 1 is the following. So you have input n, output is x0 until xn, so it will produce all your Markov chain. And at each time step, you will actually draw some kind of, we will say, candidate. So your Markov chain has xt. You will draw some yt plus 1 according to the kernel Q. And yt plus 1 is a candidate because either it fails, either it succeeds. If it succeeds, it means that xt plus 1 is equal to yt plus 1. If it fails, xt plus 1 remains at the same place, which is xt. And how can you say that it will fail or not? You will draw a random variable which is uniform on 0, 1. And if this random variable is less than this probability of acceptance, which is calculated using the current value of your Markov chain, which is xt, and the candidates, so the acceptance probability depend on these two quantities, then with this probability you accept your candidate, otherwise you reject. Okay, so this is the algorithm, and the question is under which condition on alpha, because so far there is no condition on alpha, but under which condition on alpha this Markov chain, this Markov kernel is pi reversible. So this is this problem, this interesting problem. How can we get a pi reversible kernel by imposing some condition on alpha? And actually the good point is that if you impose this condition, which is called the detailed balance condition, then your Markov chain will be pi reversible. So how do you get this? So first, there is some kind of exercise, and this exercise is to be able to draw, to obtain the exact expression of your kernel depending on alpha. Okay, and what I say to you is that this kernel, the kernel of the Markov chain, given by this algorithm 1, the kernel is given by this. You can check the proof, but we'll just look at the expression just to be convinced that it is true. So you will propose a candidate according to Q, and you will accept this candidate or refuse it. So the first situation is here, when you have drawn your candidate according to Q and you have accepted. So this quantity Q x dy alpha of xy will appear. If you have refused, then you stay at the same place. So you have a direct mass at the same place. So you start with x, so the direct mass is on x. And what is the probability of staying at the same place? Is that you have this 1 minus the integral of q x dy alpha of xy. Okay? So the real proof will be this one. We will do it during the course. But once you have this, then the question is, this Markov kernel is pi reversible if and only if you have this condition, which is a detailed balance condition. Okay, so just to check if it is true, you have to check the pi reversibility. The pi reversibility, if you go back to the definition of it is something like this. Okay, it is something like this. It is here. So pi dx p of x dy is something which is symmetric, which is with respect to x and y. If you want to check it for this kernel, so you have to look at this quantity, pi dx p, so this kernel, x dy. Is this measure on x and y, is this measure symmetric with respect to x and y? So you have two terms here and here. And it turns out that the quantity with the direct mass is always symmetric. So the quantity with the direct mass is always symmetric. It is what is proven here. Okay. So finally, if you want something which is symmetric with P, and knowing that this quantity is always symmetric, then you will get the necessary of insufficient condition that this quantity should be symmetric with respect to x and y. Okay. So this is the proof of lemma 2.4. Just to check that 2.6 is okay, we will have to check this quantity, and this will be done during the course also, so you can check it either directly on the lecture notes, or we are going to do it during the course. And once it is done, so we are happy. We just need to find some good alpha which satisfies the detailed balance condition. And here you have a lemma which tells you that at least there are two solutions for acceptance probability, either this one or this one. So this one, the first one, is the one that is commonly used in Metropolis Hastings algorithms. Why? Because it's the probability which is the highest, actually. It means that if you take any acceptance probability which satisfies the detailed balance conditions, as soon as you have fixed your proposition kernel Q, then you can show that alpha is necessarily smaller than the alpha of the Metropolis Hastings. Okay? To see it, we can look at the proof, because it's quite easy to make the proof. So assume that alpha satisfies the detailed balance condition, so it means that you are here. Assume that you have this thing. So what you obtain when you isolate alpha of xy is a ratio, pi y q of y x divided by pi x q of xy, and multiplied by this quantity, the alpha of y x. But alpha of y x is smaller than 1. So this quantity is smaller than pi of y q of yx. Since it is smaller, you will get that alpha of xy is smaller than this. So you have two bounds. First, alpha is an acceptance probability, so it is always less than 1. And second, it is less than this. If it is smaller than these two quantities, it is smaller than the minimum of these quantities, which is exactly alpha mh. Okay, so this is nice. You can get that alpha mh is the highest probability of acceptation that you can obtain. So most of the time when we speak about Metropolis Hastings algorithm, we just consider that the probability, the acceptance probability, is defined by this this quantity. Okay, by this quantity here. Okay, so this is said in this sentence in bold here. This sentence, the implicity is associated to the acceptance probability alpha h. So two examples are important. The first one is the independent sampler here, and the second one is the random walk Metropolis Hastings sampler. So the independent sampler is just that in the proposition, you just take something which does not depend on x. So you will propose something which is always the same distribution, even if your Markov chain is at some point or another point, you will propose a candidate irrespectively of the position of your Markov chain. So that's why we call it independence sampler. In that case, the alpha mh becomes this quantity, and the Metropolis Hastings is called the independent sampler. So another important example is when you propose a candidate y, which is actually xk plus some epsilon k, where epsilon k has some density q. So in that case, the kernel, the proposal kernel, can be written as q of y minus x. And if you assume that q is a symmetric density, symmetric density means that Q of x, say, is Q of minus x. Okay? So at each time step, you have this kernel. And if you look at the proposition, Q of yx and Q of xy are the same because of this property, and just cancel out in the ratio. So you just have an acceptance probability which simplifies, which is the minimum between the target at y divided by the target at x. Okay, so here is another way to write the proposition update. So here you have eta, so epsilon is eta. Okay. Okay. Let's go on. So uniqueness now. Uniqueness, there's a nice property which tells you that if you want to show that Markov kernel has a unique stationary distribution, then actually if you want to show this, you have some very nice proposition which will be proposition 2.10. Okay, so proposition 2.10 is the following. If you can find out some measure mu such that any set A satisfying mu of A is strictly positive, then for all x in the space there is some index n such that the probability to go from x to A using the kernel P n times is strictly positive. So there is a non-null probability when you start from any point of your state space. There's a non-null probability that if you wait sufficiently long, you will have a positive probability to go into A. So it doesn't mean that this probability is 1, it just means that it is strictly positive. So as soon as you have that, then you can show that P admits one invariant probability measures. Okay. So let's look at the proof. Actually, the proof is by contradiction. So you first assume that there are two distinct invariable Markov chain. No, two distinct invariant probability measures here. And according to some lemmas that we are going to prove during the course, we will show that if there are two distinct invariant probability measures, we can always find the existence of two distinct invariant probability measures that are mutually singular. Mutually singular means that there exists a set A such that pi 1 of A is 0 and pi 2 of A complement is 0. Okay, so pi 1 of A is 0 means that pi 1 is charge A complement, and pi 2 of A complement is 0 means that pi 2 charge A. Okay, so they are charging not the same sets. So assume that you have two invariant probability measures that are mutually singular. So what can we say? You take pi I and you look at this sum, the sum of Pn of xa. So what you know is, because of your assumption here, you know that this quantity is always strictly positive. So you integrate with respect to pi I something which is strictly positive. So it is strictly positive. But now you have this sum of non-negative terms. So it's sum of non-negative terms you can interchange the integral and the summation. And when you interchange the integral and the summation, then you obtain here the sum from 0 to infinity of the integral of pi I dx Pn of xa. So this is exactly pi I Pn of a. But pi I is invariant, so pi I Pn is just pi I. So you sum from 0 to infinity pi I of a, which is a constant. So this constant must be non-null, otherwise this sum wouldn't be strictly positive. So pi I is strictly positive, so we are happy. Why we are happy? Because what we know is that there is some A which satisfies this. Okay? And if you look at the contraposed implication here, you have mu of A positive implies pi 1 positive, and mu of A positive implies pi 2 positive. So the contrapose tells you that if pi 1 of A is null, mu of A is null. Okay? So we know that pi 1 of A is null, so it means that mu of A is null. We know that pi 2 of A complement is null, so it means that mu of A complement is null. So mu of A is equal to mu of A complement is equal to 0. So this measure mu is a null measure. It's contradictory with the fact that we have a non-null measure here. Okay, so this proposition tells you that as soon as you can show this, then your Markov kernel has at most one invariant probability measure. Okay, so we are happy with this, but what about Metropolis Hastings? We have seen that Metropolis Hastings algorithms are reversible, so they have pi invariant, but is pi, this invariant probability measure, is this the only one? Is this the only invariant probability measure? And then the answer is yes, thanks to this proposition. When can we get that? Recall that you have this assumption: pi has density with respect to lambda, and Q has a density with respect to lambda also, and these two densities are strictly positive. Okay, if they are strictly positive, it implies, if you look at the definition of the acceptance probability, it implies that alpha is also strictly positive. Now, if you look at P, the kernel P, it satisfies this inequality. So remember that the kernel P has two components. One is direct mass, and the first one is Q alpha. So you have this first component, which is Q alpha, and so it is. Sorry, it is the integral over A here. So P of xa is larger than this quantity, which is strictly positive. Okay. So the fact that lambda of A is strictly positive tells you that this quantity will be strictly positive. So P of xa is strictly positive. So we get this condition, but we don't even need to take any n. We can take n equal to 1 only, because P, we have directly that P of xa here is strictly positive for Metropolis Hastings algorithm. So we are happy with that, because Now we have algorithm, metropolis testing algorithm, such that kernel, the Markov kernel, the associated Markov kernel is pi reversible. It means that it is also pi invariant. And we have seen that actually under very conditions which are very easy to satisfy, this invariant measure is unique. Okay, so let's look at what you can, the take-home message. Now, if you study this chapter, you can understand the link between reversibility and invariant measure. If I ask you, can you check that metropolis testing are reversible? You are able to do the proof. So just look at the proof and try to do it again. Now you understand the form of the acceptance probability. It's linked with the detailed balance condition. So you understand where it comes from. You have seen two examples, the independent sampling and the random walk metropolis testing. And finally, you have also proposition 2.10, which gives you a way to check that an invariant measure is actually unique. Okay, so once we have done all that, I think that we are done with this chapter 2. Thanks for your attention.